So we talked about, we kind of used the ideas of probability for the likelihood function. When remember we have this P of y given y true and all of this. But for Bayesian analysis, the probabilities are even more important. So the thing I want to start off with is just talking about probability itself, right? And there, so for example, when I write something like P of y given, I'm going to call this an I over here. So this is what's known as a conditional probability, right? Where it's actually a conditional probability density. So the probability of y, some continuous variable, given I, which is whatever information you have about that variable. And the main thing to know about this, so there's, this is a continuous probability. You can also talk about discrete probabilities, like the probability that my coin toss will land heads. That's a discrete probability. Whereas this is like the probability that my continuous model parameter lies somewhere, that my continuous data lies somewhere. And when we use this this probability density, or probability density, what we're really saying is that this is a function where if I do the integral from minus infinity to infinity of dy, that equals 1. So this is kind of the fundamental piece of the definition of these probability distributions. And the interesting thing is in this, you know, anytime you're doing physical science, it's always good to remember your units, right? I remember when I took the GRE, the graduate record exam, about half or 2/3 of the questions you could just answer if you look at the units. There's only one of the 4 responses that had the right units, so it's just a trick to ace the graduate record exam. You just look at units. But it's really important because, you know, a lot of times if you look through papers, the units will be off, and it's just an easy way to recognize that something screwy is happening with the equations. So anyway, so what are the units of this? So let's say y is a distance. We're measuring the length of a rod or something like that. Y is a distance. What are the units of P of y given I? Yeah, it's 1 over y. So this would be, if this is say meters, something like that, then the probability is 1 over meters. And this generally holds. You know, if you're looking at probability densities, the probability densities are they're units that are the reciprocal of whatever that probability is. So given that, thinking about units, what does this mean? Integral from negative infinity of P of y given I di. But this is a meaningless expression. Right? You're integrating something that's units 1 over meters over some unknown parameters. So if you ever find yourself writing something like this or thinking about something like this, you're wrong, right? This is a meaningless expression. So, but you're right. We will at some point we will be integrating over this di, but we have to integrate something different over the di. This is not something that can be integrated over di. But your intuition is correct that we're integrating over we're trying to integrate somehow integrate over the parameters of the model. But this is not the way to do it. Right? So yeah, so let's erase this. So this is a probability. And we saw earlier something else, kind of an extension of this. If we saw something that looks like this, P of x comma y given I. Now, let's think a little bit about what that means. This means probability of x and y, so two independent, or not necessarily independent, 2 different measures that we're asking what the joint probability, the probability that they're both the same given piece of information. One thing I meant to say, if you're looking at this P of y given I, really what this is a probability of density. So actually to convert it to a probability, you need to do something like P of y given I times some delta y. Now what you're saying there is that if this is our P of y given I, we have some probability density like that in y. And what we're asking is what's the probability that y lands in this little delta y bin right here, right? So we have to kind of, if we're going to convert the probability density into real probabilities, we have to specify a little interval, right? Yeah, probability is unitless, and so yeah, we take this, we multiply it by some little interval with length meters, and then what you end up with is a unitless probability. So anyway, I just wanted to say that. So back to this joint probability, P of x and y given I. So if x and y are both distances, what's the units of this probability? Yeah, 1 over meters squared, 1 over distance squared. So just like it's the reciprocal of this, here it's the reciprocal of this times the reciprocal of that. That's the units you're working with. But let's think a little bit what this means. If you think about one way you can visualize this is kind of a Venn diagram. So let's say we have this box, and this represents in some abstract way the parameter space allowed by I. This information is kind of a slice of parameter space that's allowed by I. And we say that x is somewhere in here, inside here is x, inside here is y. And so our P of x and y given I is this intersection region right here. Right? Now, looking at this, you can start to think. You can start to think about how you might, with this visual representation, you can start to think about how you might manipulate this expression a little bit. So, essentially, the way to think about this is that the P of x and y given I is, in this representation, it's like looking at the area of x intersecting with y divided by the area of I, right? That's one way to visualize how this is working here. So, how do I want to say this? I had something in mind here. I had a reason for saying this. And it'll come to me. Oh yeah, so what if you factor this out, right? You could say that this little area here divided by the area of the whole thing. Another way you can express that is you could say this is the area of x and y divided by the area of y, and multiply that times the area of y divided by the area of I, right? So you're just we're just expanding this out by multiplying by 1, right? And this A of x and y given y, what that represents is the P of x given y and I, right? So we're basically saying, given that y is true, what's the probability of x being true as well? And we're multiplying this by the probability of y given I. So the probability that y is true given everything, and the probability that x is true given y. So what we've derived here is kind of, it's a hand-wavy way to do it, but it's a good way of thinking about probability. What we've derived here is the expression for conditional probability. So this joint probability of x and y, is equal to the probability of x given y times the probability of y. So this is one of these fundamental things that's really important, and it's so important that I'm going to erase our picture, keep that in mind, and I'm going to write this up here. So probability of x given y, comma I, times the probability of y given I. And this comes from, this is actually the definition of joint probability. And you should memorize this, because as you manipulate probabilities, as you're going through this, you'll come across this sort of expansion all the time. You have the conditional probability of x given y times the probability of y is this joint probability. Now, one thing that's interesting with this is that this is completely symmetric, right? So just as we did the probability of x and y, we could do the probability of y and x, right? It's just the same thing. You flip the signs. But if we do the probability of y and x, we can expand this in a different way, right? So we can say this is also equal to probability of y given x and the information times the probability of x given the information. So this is just another way to expand these things. And now, thinking about the equivalence of these two expressions, we have something really interesting that when we interpret it the right way, as you'll see, it gets pretty profound. So, putting these together, I'm going to set these equal to each other and divide by probability of y. So, and then we end up with, somewhere here, p of x given y and I is equal to the quotient of p of y given x and I times the p probability of x given I, all divided by probability of y given I. So this is a really important result. It's somewhat intuitive. It's just basically saying that joint probability is symmetric. It's another way of saying that. And this is known as Bayes' theorem or Bayes' rule. So anytime you do a Bayesian model fitting, it's basically built on this right here. Is that clear how that was derived? It's kind of this, just noticing that the joint probability is symmetric, you express it in a different way and you pull this out. So this, and Bayes' rule is in some ways really simple, but in some ways really, really profound. Make sure I did everything that I wanted. Yeah, so this is Bayes' rule. And now where this gets a little bit profound is if we start relabeling things. So let's say instead of, I'm going to take all the x's and I'm going to replace the x's with thetas. So we'll do theta there, and those are the two x's. Oh yeah, thank you. I just couldn't read my own x. So those are the x's, replacing them with thetas. And let's make the y, let's replace that with a d. So d will represent data. All right? So now what we have when we replace those parameters now, we're used to thinking of theta as model parameters. These were the slope and the intercept earlier today, right? And d would be the set of the x and y values. So let me just write that out so we can see. D would be like xi, yi, sigma I. So that's the data that we know. And theta would equal m comma b for our linear model right here. And now you see that this is a little bit profound, right? So now we're saying, what we've computed is we said, given our data that we've observed, what's the probability distribution of our model parameters? And this equals some expression that's the probability of the data given the model parameters times the probability of the model parameters divided by the probability of the data itself. So are we all clear right there? So this is the basis of Bayesianism. And the insight of Bayesianism is what you want to do when you're finding the best fit model. Essentially what you're saying is you want to maximize the probability of your model with respect to the data, right? So this is the thing that we're trying to solve in Bayesianism. And these different terms have different labels. So this right here is known as the posterior. And you can make all your sophomore jokes about maximizing your posterior or whatever you want. And this right here, does anyone recognize this term? This is a likelihood, yeah. So this is exactly what we computed right here, right? It's the probability of all the data given the model. So this, we will call this the likelihood. And any guesses as to what this one is? This is the prior. So this term right here, the prior, is one of the places where this gets a little controversial. So what does the prior mean? What in words, what would you say is probability of theta given information? What does the prior mean? Prior knowledge, your first guess, yeah. So essentially what this is saying is what's the probability that your model is correct, given that you don't have any data yet. So like before you start the experiment, let's say you want to measure the mass of a black hole in a galaxy, and you have some sort of radial velocity data or whatever that'll help you do that. Before you even turn on your telescope, before you go up to the mountain and gather data, this says you need to know what the probability of the mass of that black hole is. So this is what strikes some people as a little bit anti-scientific, right? Because you're supposed to be completely agnostic. Before you gather the data, you're not supposed to make any claims about what you're measuring, right? But if you're going to do this in a Bayesian sense, if you're going to do model fitting in a Bayesian sense, the prior is required, and you can't ignore it. And so this prior, this is really interesting. And this last term right here, this might seem like it's another thing that's very interesting and very controversial, but it turns out you basically ignore this all the time. And the reason you can ignore this is because this is just equal to the integral of the numerator. So P of D given theta I times P of theta I. Yeah. PD. So essentially this is, because this probability needs to be normalized, you need to be able to integrate this over theta and get 1. This quotient here is just this denominator is just an integral that allows this to be equal to 1. It's a normalization factor. And there are situations where you need to compute the value of this, but like 95% of the time, if you're computing this, this is often called the evidence. 95% of the time, if you're computing the evidence, you're doing something wrong. This is really hard to compute. And I mean, think about what you're trying to do if you compute here. You're integrating the probability of the data over all possible values of the data, right? So if you make 100 observations of something out in space, this is a 100-dimensional integral, right? Over all possible values of those data multiplied by your model prior. I mean, this is just almost ridiculous, right? It's hard to imagine how this would ever be computable. And it turns out it is computable, and sometimes you need to compute it, but most of the time you just want to ignore that. So these are the four pieces of Bayes' theorem: the posterior, the likelihood, the prior, and the evidence, which usually you ignore because it's just a normalization. It's true. You want just ignore the evidence. It doesn't matter. Yeah. So the interesting thing here is that if your idea, what you try to do is maximize this posterior. That's known as the maximum a posteriori theta. So maximizing the posterior would give you this theta MAP, which is maximum a posteriori, maximum of the posterior. That gives you, it's essentially maximizing the likelihood multiplied by the prior, right? So you'll see this all the time. The MAP estimate means the maximum of the Bayesian posterior. So how do you turn a Bayesian estimate into a frequentist estimate? How do you make the Bayesian estimate match the frequentist estimate? Well, not with no prior. You need to specify something here. But what do you? Flat prior. Yeah. So if you say here's my theta, and here's the p of theta given I, and you say it's some flat number between a lower limit and an upper limit. If that's your prior, then the Bayesian estimate is equal to the frequentist estimate. And so this is interesting, and this is where arguments start. It's really fun because Bayesians, a frequentist would say, I don't need this. You Bayesians are ridiculous. Why do you need this prior information? The prior information biases your values. You have no source to actually come up with a prior. It's just like throwing weird terms into your expression, right? And the Bayesian says, well, you guys are using a prior. You just didn't tell us, right? You're implicitly using a flat prior if you're doing maximum likelihood. And the frequentists come up with some explanation where they say, no, it's not actually maximizing the likelihood. There's a likelihood principle, and you can do all this stuff. And Bayesians say, well, I don't care. The prior is right there. If you're actually talking about the probability of theta, you need to specify the prior. And this is where this interesting thing comes in. So a lot of people will treat the likelihood, this probability of data given theta, they'll treat that as a probability distribution in theta. Right? It's really tempting to do that. When you write this whole thing out, you get a function of theta that sort of looks probability-ish, right? And you'll treat that as a probability. But a Bayesian would come along and say, no, this is not a probability for theta. This times the prior is a probability for theta. But you can't ignore that prior, right? So this is the distinction between frequentism and Bayesianism. Bayesianism looks kind of probabilistically at it's sort of like a from first principles approach, right? We start with the definition of probability and we step through and we ask, what's the probability of our model given the data that we've observed? Whereas a frequentist says, well, here's this likelihood, there's a likelihood principle that says that contains all the relevant information, so I'll just work with that. So anyway, this is where you mentioned that there's one place where frequentists get uncomfortable. And it turns out that what that comes from is the definition of probability. So what a frequentist says is that probability is based on frequencies. Right? So what is the probability? When I flip a coin, what does it mean to say there's a 50% probability that it'll land heads? A frequentist would say what that means, so philosophically what that means, is that if you flip the coin 1,000 times in a row, you're expected to get something like 500 heads, or plus or minus a few. So a frequentist would say that is what probability means. You need to repeat the result, and in the limit of a large number of repetitions, the probability is the frequency of certain results divided by the total. Right? A Bayesian would say, no, probabilities have nothing to do with frequencies. Probabilities are something more fundamental than that. When a Bayesian says there's a 50% probability that this coin will land heads, they say that is an expression of statement of belief. So, right, the Bayesian says, I'm 50% confident, given my own model of the universe and the model of this coin, that one flip of that will land heads. I'm 50% confident that it'll land tails. So, this point is it's really interesting, because what that says is the Bayesian can make a probability statement about something that happens once, right? On a single coin flip, the Bayesian can say I'm 50% certain it'll land heads, 50% that it'll land tails. A frequentist, if you have a single coin flip and no possibility of repeating it over and over, if you have something that can't be repeated, a frequentist would say, I can't make probability statements about that, right? So, for example, let's say, imagine you're trying to find the density of matter in the universe, right? But multiverse hypothesis aside, we have one universe to work with. And in some senses, it's meaningless in the frequentist sense to say the probability that omega matter is 0.3. Because we only have one universe to work with. You can't repeat that and measure that quantity or have that quantity happen over and over again. But the Bayesian says, no, that's just fine. It's just probabilities. We're talking about degrees of certainty. So this is a bit of a fine point, but does that make sense? Frequentist probability is frequencies of repeated events, where Bayesian probability is degree of knowledge about individual events. And this is where the whole thing breaks down, right? Because if this is our model, say our theta is the slope of the line. This is a little bit abstract, but let's say theta instead is the mass of the black hole in a neighboring galaxy that we're trying to find. A Bayesian would be able to say something probabilistically about that, right? This black hole has a mass of 10 to the 9 solar masses with some probability. And that's a statement of degree of certainty. The frequentist, you can't say anything about that individual black hole probabilistically, because there's no way of repeating, how do you repeat this galaxy, this one galaxy? So a frequentist would say this statement right here, this statement of the posterior, this expression, is fundamentally flawed. So the frequentists would say that. And that's because these model parameters, these thetas, are, to the frequentist, it's something you can't express probabilistically. You can't repeat, you can't repeat the universe in order to find whether there's a probability of this. You can't say there's a probability of omega matter being 0.3, because omega matter is a quantity, it's a fixed quantity. You can't say there's a probability that the mass of the moon is some value, because the mass of the moon is the mass of the moon and nothing else, right? So that may have gotten a little bit philosophical. Does that make sense? We could go into the philosophical details of probability and argue about this forever, but this is the fundamental difference. The Bayesians are looking at probability of model parameters, where frequentists say model parameters are fixed. You can't make probabilistic statements about them. You just have to make probabilistic statements about data, about things that can be repeated. Your measurements can be repeated. Awesome. Now I think we can move on, as long as you understand that what we're doing here is we're trying to get the probability, which is a degree of knowledge about our model, given the data that we observed. And so if you think about it that way, if you kind of suspend your frequentist disbelief about this, we can move on with that. So the question is, given this, how do we solve this problem? Right? We had this nice, for this likelihood when everything was Gaussian, we had a nice closed form solution. But then we have to add the prior, so how do we do this in reality? And let's go back to, I'm going to erase this down, and let's go back to our straight line fit. So here, again, our data is xi, yi, sigma I. And our model is M and B, the slope and the intercept. So if we're going to do this, if we're going to compute the posterior, we have this, which is likelihood. That's easy, we already did that. It's the same as the frequentist result. Multiplying by the prior. So what prior might you use? If you were trying to do a straight line fit here, what are some options for the prior on theta that you might use? One of them we saw, flat prior, which is basically repeating the frequentist result. We say that it's proportional to 1, basically. What are some other options we might use for the prior? Yeah, that's a great point. So I wrote P of theta given I equals 1. What happens if you plug that into here? You get infinity, right? This is an unnormalizable probability. But the funny thing is that in practice, a lot of people use this. And this is one thing where frequentists, so my archetypical frequentist is this guy named Phil Stark, who I know he's the head of the statistics department at UC Berkeley. And we've had some great arguments together. Because his main point about why Bayesianism is a bad approach is because he says, even if you try to express a prior, you always end up with these unnormalizable priors, these improper priors. And the way the Bayesians get around this is they say, well, the way the Bayesians get around this is they say that it's, let's say, this equals 1 over B minus A for A is less than theta is less than B, and 0 otherwise. So then what you're saying is you have, if you integrate this, it equals 1, and then, your prior looks something like this, as some like box function, and as long as the likelihood here, as long as the likelihood has some form that looks like that within it, then your prior is essentially flat. So it's easy enough to have these limits. Like you're measuring the length of a rod in your laboratory, and you say that the prior is it's somewhere between 0 and the distance from here to the moon. You'll be all right. It's effectively a flat prior. So we basically say it's proportional to 1 with this caveat that we have to make it normalizable somehow, but it usually doesn't matter. So that's a good point. We have flat priors are improper, but we can do some hand wavy stuff to make them proper priors. So what's something else you might do for this prior on the slope? So this slope might be something like the relationship between the mass of a black hole and the scatter of the velocity in the galaxy, right? So we might have some actual prior information, right? There's actual prior measurements of this slope of the black hole mass and scatter relationship. So we could actually put in actual prior results. So that might work. Then you have to think about things like, do I actually trust the prior results? I'll use this if it was my paper, but not if it was my competitor's paper, right? Or something like that. So these are kind of the two types of priors people use generally. This one is trying to be, in some senses, uninformative. So we have this uninformative prior, and this would be an informative prior. So this is one that adds some sort of real information, and this is one that attempts to not add any information. Does anyone see a problem with this though? Calling this, and this is maybe an unfair question because it's a little bit difficult, but is saying the probability equals 1 really an uninformative prior? I mean, if you think about this here, think about this in terms of the slope. So if we say the prior probability of our slope, given whatever information we have, equals 1. So that means that the probability that the slope is between 0 and 1 is equal to the probability that the slope is between 10 to the 6 and 10 to the 6 plus 1, right? Basically say each unit of the slope is equal probability. So you translate that to the graph and you say that the probability that the slope is here is equal to the probability that the slope is here, right? So we're essentially like this flat prior on our slope is biasing us towards small slopes, right? It's biasing us towards this quadrant of the graph. Yeah, so that's one thing you can do. You can say, well, you know, the slope is kind of biased to whatever this is. What I could do instead is say that let's make this an angle phi. So I'm going to translate coordinates so that the probability of the angle phi, which is equal to something like tangent inverse of m given I equals 1. And so you do a uniform prior and some translation of variables. And it turns out that if you want, for the slope, if you want a uniform prior, or if you want a non-informative prior, this is much closer to what you actually do than putting a prior on the slope. Right, so there are, I have a blog post series on frequentism and Bayesianism where I actually go through the arguments on how to do that. I'm going to skip that right now in the interest of time. But so sometimes coordinate transformations, and in particular symmetry arguments in your data, can give you a real informative prior, where the flat informative prior might not be reasonable. But the thing that in practice, though, you know, we argue about all these priors. In practice, though, let's take a look at this. What does the arctan look like? I got to draw arctan. It's something like this, right? I don't know. Let's just pretend the arctan looks like that. So this is the arctan prior, and this is the flat prior. The only time this really matters is, let's say if you don't have very much data, your likelihood looks like that. So this is L with no data, or not much data. And then if you have a lot of data, your likelihood kind of looks like this, right? So this is lots of data. So the argument that Bayesians will make is that the prior only really matters when your model is not well constrained by the data. But as soon as you have enough data to really specify your model well, the effect of the prior goes away, right? This slope here doesn't really change much compared to just the flat line there. But it's only when we're looking at a large, wide likelihood where we don't constrain the data that we get that. So I feel like I'm spending a lot of time kind of arguing the finer philosophical details, and I want to make sure that we get to the point of actually computing this. So let's just, this is the type of prior we can choose for these lines. These are the types of thinking we go through. Right? It's either uninformative or informative, and if it's uninformative, we want to make symmetry arguments or actually think about what the model means to figure out what it is. You know, variable transformations and things like that. But in the end, if you have enough data, the prior really doesn't matter. Okay? So now let's think about this. What do we do once we have this? We have this ability to compute the likelihood as a function of theta, the prior as a function of theta, and then we have this posterior distribution that might be a high dimensional object. And difficult to compute, difficult to integrate the whole thing. And the way that in Bayesianism we handle this usually is to do sampling. So we have, where should I write? Again, whiteboard management. What am I doing here? I'm going to erase this thing about the prior. So let's say we have a posterior that looks like this. This is just a one-dimensional representation. We might actually have this is a function that at each value of theta, this is p of theta given data I. At each value of theta, we know how to evaluate what that posterior looks like. If we have a really, really high dimensional function, in general we do, we have maybe theta 1, theta 2, theta 3, theta 4. Just imagine this being like a 5, 6, 8 dimensional graph, something like that. For a high dimensional function like that, it's really, really hard to maximize, to optimize this. And so what Bayesians tend to do in this case is to do a sampling. So we design an algorithm that samples points from this distribution so that as those points are sampled, their histogram will mimic the distribution itself, right? So, as we sample points, I'm sort of being sloppy here, but the distribution of points will look kind of like that. So I want to show you the posteriors. We got to get back to the computer and do some actual calculations. So I want to show you what it looks like for a Bayesian to do this sort of model fitting using a sampling distribution. So here, let me clear and just make sure I'm actually executing everything here. So again, here's our data. Let's make this bigger so you can see. Here's our data with the error bars, right? And we know how to construct the likelihood here. It's just the product of the Gaussians, the individual Gaussians for each data point. And then we write Bayes' theorem like this. Notice I've used a constant of proportionality because this is going to be unnormalized, but we don't need to normalize it for this procedure. And the way that we do in practice, the way that we do Bayesianism is to do this sampling on the distribution. And there are things called Markov chain Monte Carlo samplers. And this is like, if you're into Bayesianism, Markov chain Monte Carlo, it's MCMC, it's the algorithm you use for everything. And there's this particular package called MC, and let me pull up the web page for this because it's rather entertaining. Where's mine? Yeah. So that MC package is by Dan Foreman-Mackey, who's one of Dave Hogg's grad students. And I love the tagline, it's the MCMC hammer. He calls it seriously kick-ass MCMC. Basically what it is it's a package that does sampling of posterior distributions so that you can do this sort of calculation. And this is what we're going to use, and this is what I use for lots of different things. So the way that you use MC is you have to define a function that evaluates the posterior. So here we have the model, which is what we've seen before, mx plus b, right? I think I switched m and b in this compared to earlier, but that's all right. We're going to say the prior, we're going to define the log prior, which is 0. So essentially we're choosing, even though it's somewhat ill-advised, we're choosing this answer. The prior probability equals 1, so the log of the prior probability is 0 plus a constant, something like that. Then we're going to define the log likelihood. So this probably looks familiar too. This is just the log of what we computed before. You have minus 0.5 times the sum of this thing that's out front involving 1 over 2 root 2 pi sigma, and then the y minus y model squared over 2 times the error squared. So that's our log probability, log likelihood. And then the log posterior is just the log of the prior plus the log of the likelihood, right? The multiplication turns into division, or turns into addition when we take the logarithm. So defining that, now the way the MCMC works, the way the sampler works, is we take these details you can read through, but we're basically taking a number of starting guesses, and those starting guesses will, kill that. from the starting guesses, this procedure goes through and generates points that are distributed according to this posterior, according to this distribution. And what we get out is this chain of points, and that chain of points you can think of as a bunch of draws from the distribution. And when we have those draws from the distribution, we can do things like compute the mean of all those points. And the mean of all those points will be, if we have a symmetric distribution, will be somewhere near the maximum, right? Near this maximum a priori. And there are reasons, maybe I'll get into, I don't know. There are reasons that the mean is a better estimator than the maximum in this case. So once we run this, we're running this, and this is creating a sample of the distribution. And if we plot the sample, this is what it looks like. We have the, actually let me get a full screen again so I can get the whole thing on there. This is what it finally looks like. We have what's called the marginalized distribution of the intercept here. So we've kind of integrated out the slope, and this is the probability of the intercept. And up there we have the marginal probability of the slope, and then in this two-dimensional parameter space, this is what this looks like. This is what the sample is. So once you have that sample, you can kind of see what the posterior distribution looks like. And so in this case, the slope and the intercept, the maximum of the posterior is right there in the center. And by integrating these, basically integrating them by taking the mean of all the points, we can get an estimate of the line. So then here's the sample. We're going to take the mean across the 0 dimension, and we get something that looks like that, a slope of pi. That's weird. And an intercept of minus 2.7. And we plot the result, and we get something that looks like that. So this is the Bayesian view of fitting a model, fitting a line to data.
Can you say again how you decide which values to use?
Yeah, so where we go from the sample to actually getting the values is we take the mean of all the points. So the mean of all the slope values here is essentially getting the mean of mean of all the slope is like getting the mean of that distribution up there, which for Gaussian is close to the maximum, right? And so taking the mean of all these values gives you something in the center of that distribution. And taking the mean of all these values gives you something in the center of this distribution.
Are you saying these are Gaussians as well?
In this case, they are Gaussian, yeah. That's because basically because everything we put into it, we made the prior equal to 1, so we're just integrating the likelihood. And the likelihood is Gaussian, and that's why we could do it closed form before. But in general, this won't be Gaussian. You might have seen like cosmology papers where you're looking at the dark energy equation of state versus omega matter, and you get this kind of banana-shaped distribution, right? So anyway, I hope I haven't. What was I going to do? Oh yeah, this is what I meant. So looking at the mean, this is like, that's just a single value that comes out. We're used to wanting to have a single value for the slope. But in the Bayesian sense, the answer to the problem is not a single value. We're not asking for this maximum for the posterior. In the Bayesian sense, the answer is the posterior PDF. This is saying, given everything I know about the universe, given the data that I've measured, what I know about this model is this probability distribution over the parameters. So one cool thing you can do with this is instead of taking the mean of the data, you just take a sampling of maybe 100 or 200 points, and you plot all the possible slopes. So this in a sense gives you some information about the uncertainty involved in the model. So you can see the way that I did this, instead of taking the mean and plotting it, I go and I choose 200 random indices. So I take the range of the number of samples, and I use this random.choice, and I choose 200 of those. And then I plot the data, and then for each of these indices, I plot whatever those sample parameters are. So I'm choosing one of the points from this plot right here, and plotting that. I'm using this alpha, so this is a transparency index. And this I think is really cool. This is one of the great parts of Bayesianism, is you automatically get out this model uncertainty in the sense of, your probabilistic knowledge about the models.